Okay, constructability. I think this might be kind of quick. I think I've kind of generally been discussing perfect projects, which we try to avoid. It's good to have practice and it's nice to have low liability, but ideally we can take marketing. I was trying to turn all this flex black, but I'm gonna give up on that, okay, sorry. Ideally we can have marketing photos and then, you know, have something to be proud of too. So we wanna build the projects, so let's make sure they're constructible, and to do that, it does take a lot of effort and a lot of trying to just consider the other trades. So that's a large part of it. So the sizing of the equipment on the floor plan, the way that's commonly done is by leasing competitively bid projects where you have three manufacturers, as you take the worst case dimension for all the widths and everything. And that way you're sure that there'll be enough space. Even for the underground coordination, just if you have long radius elbows underground, that can really push you down further than you thought. And then you just want to go whoop on the other side of the wall, and now all of a sudden the contractor is sending you a request for information. And yeah, structural, likewise, when we're going across some of those structural foundations, those are spots that, at least in specifications, we end up changing to rigid metal conduit, galvanized, or it's the considerations of where we're stubbing up. It's the knowing of that whichever trade gets there first is probably going to start installing first. So they might have, if you want to go do your above ceiling inspection, you might want to get there first. Bonding and grounding, it's making sure you're out there for these things too during construction administration, when they're doing those coordination of the other trades and disciplines as well, right? You want to make sure if the mechanical has a certain size horsepower motor, and or that they didn't say who's going to provide the motor starter. Constructability, the concept is broad, and but it's important. Okay, no questions on that one. I'll continue. Power calculations, basics of electricity and safety. So not in a sense such that, like, going through engineering school, there is calculus and all these things, and of course those things are good because they help you become a better problem solver. But there's not, so from the sense of complexness in this electrical engineering consulting, there are certainly firms that go after complex projects, and then maybe you're working with some of the laboratory designers or something, and you're thinking about complex topics, and grounding and bonding, and those things are all complex. But I guess I would just say that there's not quite a bit of needing to know the intricacies about electricity to just be a consultant, but to be caring about safety and to be knowledgeable about what should happen during commissioning, and considering how technology is continuing to evolve, especially in wireless as well. It's important to try and just be sure that there's not an absence of technical understanding of the fundamentals of electricity. So what's shown here is just to put your mind in that realm and know and remember that what we're discussing is physics. So here's our AC, right? It goes up and down. AC goes up and down. DC doesn't do that, right? It's just, it's consistent. It doesn't go back and forth. It goes one way. In order to transfer from AC to DC, such like in the wall wart, when you plug it in the wall, because that then delivers DC to your electronics, there's an AC to DC conversion process that there's various ways to do it, but there's little electronic diodes, for instance, and capacitors that slowly turn up the waveform such that it can't be positive and negative anymore. It's only positive, and then it smooths it out to get that DC. And the physics of it is quite literally electrons jumping chairs. So when we provide a potential such that a electric motor turning or generator turning with an alternator associated and a rotor, I see the stator and the rotor here, a permanent magnet generator, we are creating an electric field. And when you create the electric and magnetic field, you can generate current, which means you can make the electrons jump. So for instance, inside of a fan, inside of your, like a fan at your house, whenever you're doing this, what you're doing is physically changing the coils. So there's inductance and the concepts of AC electricity. So an AC power transformer that steps the voltage from a high voltage to a low voltage does so because there's a coil and another coil, and there's 3 of them, and they are just transforming the voltage without contact to a different from a higher to a lower voltage, or vice versa, which isn't done in DC because the inductance, which happens by having those coils close together, isn't performed. So to change DC, it's more resistive heat loss. So in the term of heat loss, we have electrical equipment in rooms, especially if we have a lot of it. Our mechanical counterparts, the disciplines, are very interested in helping us because we want to make sure the rooms don't get too hot. We're also considering, if you look up major manufacturers like Eaton or Square D, ABB, GE, otherwise, they give you heat loss data for the equipment, and it depends on how much that equipment is demanded. So there's an I squared R loss situation here for this. So that's one type of calculation that we need to provide within our engineering. Load flow, we were kind of discussing with the panel schedule. So you have a panel board and things are connected to that, and then that panel is connected to another panel potentially, and then to another panel or a switchboard, and then maybe there's transforming voltages, and so there's transformers throughout the distribution. Along the way, we're finding out how much load is happening, and within the NEC, the National Electrical Code, they allow the panel that's connected with more panels to it not to have to be such that all of the individual loads were connected just to it. There's diversity and demand opportunities to make smaller services. Voltage drop, we said before, like for a garage, that was a long ways away in that example up here. Should there actually be load, if there's no load, it's not a problem. But if they do want all those electrons to jump and go over there and do work, then there could be voltage drop, and the voltage drop means you need to have a larger size wire. Nebulous LLC's also got a very good voltage drop article here that is has lots of examples, and it tries to be illustrative if there's context there for you that you're interested in. Of course, we're filling cable and conduit tray with wire. So there's calculations for that, which necessarily like 40%